Hello. Today we begin talking about hypothesis testing. Confidence intervals and hypothesis testing are the two big topics of inference. Before we get started, just a note to the AP test takers. I think we're going to be okay. Just stay on pace. Hopefully you're watching the review videos on the AP website and of course doing everything we're doing right now with our class because we're still pushing our way to try to finish the course. We will be finished before May 22nd, which is the AP exam. And so you will have had the entire course and practiced it. We won't have much time for looking at actual AP exams from the past and practicing, but you are free to look up any resources and do that yourself. But if you're doing what we're doing every day and the AP review videos, those 45-minute videos, you're doing pretty well for right now. I will try to get you some more information before the test, of course. You do need to make sure you go into the AP website and let them know that you still are taking it. They are asking all AP test takers to read the information and basically check that you are still taking it. It's going to be a 45-minute online exam, and there's more information that I will give to you shortly. Let's dive into hypothesis testing. Suppose Energizer, the battery, claims that their batteries last an average of 40 hours in a toy, so continuous. So you can test that, right? You can. We randomly got 30 batteries, put them in a toy, the same toy, all 30 batteries, and ran the toy. And somebody had to kind of sit around and watch, and then when the toy died, assuming that was the battery that died, they recorded how long the battery lasted. And here's our results. The mean, out of the 30 batteries, the mean duration was 37.6 hours. With a standard deviation of 1.3 hours. So not 40 like Energizer claimed, but pretty close to 40. I don't know, what do you think? Is this proof that they are wrong? Is this evidence that they are wrong? There's a difference there, right, between proof and evidence. Evidence is usually used to help you learn whether you have proof, but they're different. So some of you may have decided when I was talking that this is proof that they're wrong or this is evidence. Others of you might have said, you know what, there's variation in life. There's variation in batteries. There's variation in everything. Energizer could have a batch that lasted 37.6, but that doesn't just prove that typically their batteries last 40 hours on average, right? But everybody has an opinion. We're going to try to cut through those opinions using probability to help us answer these questions. Here's a different example that we're actually going to do. A claim is made that COVID-19 has disrupted at least 40% of Americans' jobs or finances. So 4 out of every 10 adult Americans, at least, this is what the claim is saying, right now they either have their job has been disrupted or their finances have been disrupted. So Gallup did a poll recently and they randomly sampled over 8,100 adults, and they found that only 32% of the sample had their job or finances disrupted. Is this proof that the initial claim then is wrong? Well, that word proof is kind of strong, isn't it? We're just dealing with a sample. Could our sample be off? So maybe we don't want to use the word proof. How about using the word, is this evidence that the claim is wrong? Or do you think 32% is not far enough below 40 to say that 40 is definitely wrong or evidence that it's wrong? Here's what we do in a hypothesis test. We start by assuming that the equality portion of the claim is correct. So the claim being made that at least 40% has been disrupted, the equality part of that is equal 0.4. So we're going to assume that, yes, 40% or more have been disrupted. And we're going to use our sample as evidence. Now, the null hypothesis, we call it, is that part about assuming that the equality portion of the claim is correct. We designate it by H sub 0, colon, and then we say whatever our population parameter is, like P in this case, population proportion, is equal to 40. That's the null hypothesis. Null comes from a Latin word which means no effect, no difference, no problem. In other words, we're going to assume that at least 40% of Americans have been disrupted. Now, there's an alternative to that. If that's not true, what's the alternative? We designate that by H sub A, and we write that as P, population proportion, is less than 40%. How do I come up with less than? Well, if the null is essentially greater than or equal to 40, even though we're only going to write P equals 0.4, the opposite of greater than or equal to is less than 40. Now you could go ahead and write the null as P is greater than or equal to 0.4. The HA would still be the same. P is less than 0.4. Now there are some specific rules for the null and alternative. You can't just put any inequality symbols you want in there. And those rules are the following. The null hypothesis must contain a condition of equality. It must contain one of those three. It has to. You can't put just a greater than in the null or a less than. If your claim is like a less than or a greater than, we'll just put it in the alternative, because the alternative is what is able to take the condition of inequality, one of those three. So if you have a claim that says, oh, less than 20% or greater than 20%, simply put that in the alternative and do the opposite for the null. Now, if there is no greater than or less than component, if it's just somebody makes a claim that something equals 60%, and you don't have intuition either way, if greater than or less than that, the alternative can just be not equal to. We call that a two-tailed test. It could be on either side of the claim. We don't know which one. So the goal of what we're about to do is simple: to collect evidence to test whether the null hypothesis is valid or not. And yes, probability comes to the rescue again, because probability is not based on opinion. It's not based on people's misinterpretations of facts generally. Probability is the chance of something happening, and we're going to use that to help us make our decision. Conditions must be checked. So these look a lot like the confidence interval conditions. There's a small difference. First of all, the first three are the same. You want to make sure you have a random enough sample. Each individual was independent of the last. You don't want your sample to be too big, because then probabilities change too much, like the deck of cards. So we call that the 10% condition. But here is what's a little bit different from confidence intervals. Confidence interval, it said NP hat and NQ hat must be at least 10. Well, now that we have a P again, we have a null hypothesis, which we're going to assume to be true, then we use it, right? So that is what, I don't think I said that yet, but we always assume the null to be true, and we move ahead using our sample to see if we can support that or not. But anyhow, since we have a P to work with, we use it. NP and NQ must both be at least 10. If these are all met, then we can use the normal model with confidence, and we can rely on our results. We're going to be finding a p-value. Now that p-value is just that probability I've been referring to. The probability that we're about to find is called a p-value, probability value. And what it is it's the probability of getting our sample as extreme or more extreme, meaning greater than or less than our sample, assuming that the null is true. So think about it. If the null is true, we're probably not going to get a sample too far away from it. If the null is false, then we're likely to get a sample that is further away from it, right? So the further away our sample is, the more evidence we have against our null hypothesis. The p-value just simply gives us a number to work with. It gives us the area of the tail In other words, how far away is our sample from our population, from our null hypothesis? Think about this. If the evidence is strong against the null, we're going to have a low p-value because that probability is going to be low of getting a sample that far away. In that case, we're going to say we're going to reject the null. If our p-value is not low, if it's relatively high, then we don't have enough evidence to reject the null. Now notice we are never going to say we accept the null. This is even used by our justice system. Think about it. Does a jury ever come out and say, we the jury find the defendant innocent? No, they don't. Think about that. You never hear that. Other people might try to say that that means that he or she is innocent, but the jury doesn't say that. The justice system understands this concept, and they never say innocent. They come out and just say not guilty. There's a difference, isn't there? If you're not guilty, it doesn't prove you're innocent. It just means that in the court of law, there was not enough evidence to say that you're guilty. You still could be guilty. That person still could be guilty. We just didn't have enough or find enough evidence. So not guilty is what we say. In this case, we say we failed to reject the null. So we never come out and say we accept the null. The null could still be wrong. So we can't say we accept it, but we can say, well, we failed to reject it. All right, the job data. Here's the work. Here's what you guys are responsible for doing. The claim was that at least 40%. So we're going to just go ahead and make it an equal sign. It's okay to do that. That's very common. The HO, the null hypothesis, null means no difference or equal, is P equals 0.4, population proportion. We're always trying to learn about the population, right? Not the sample. The alternative now is the opposite of the greater than or equal to, so that's less than 0.4. Notice we have inequality here and we have equality here. It fits the rules of HOHA. We grab our sample, we show our information from our sample, we show our sample size n. They gave us a p hat, they didn't give us an x. That's okay. They kind of took a step away from us. They gave us the p hat. If you need to find x, if you need to put it in the calculator or something, you can just take 32% of 8104 and round it, because you do want a whole number here. You have to have a whole number, number of adults that said they were disrupted. You can't have a decimal here. So we're going to go ahead and find our sampling distribution parameters. The sampling distribution, the mean of all the p hats, will center at p, and we're going to assume that the null is true. So here's a big difference from a confidence interval. Confidence interval, we did not have a p, a population proportion, to even work with. We had no idea, so we were going to go ahead and try to find it by getting a sample and making an interval. But in a hypothesis test, we have an assumed to be true population proportion. So we're going to use it all the way through our problem. So p equals 0.4. We're going to assume that's true. So that's what p equals. Our standard error also uses the p we assume to be true. We're back to pq over n. So we don't use p hat q hat for a hypothesis test here, because we assume we have a p that's true. So that's how we get 0.4, 0.6 over the n. Don't forget to square root it. We have a pretty small standard error. That's because we have a large sample size. So we have more shrinkage in our sampling distribution. This is good because the larger the sample, the tighter your sampling distribution normal curve is going to be. So you're more likely to get samples close to the population proportion. If it is true, that is, right? So now we got to go ahead and find our z-score. How far away is our sample from our population claimed to be? So we just take our 0.32, take our sample minus our population, divided by our standard error, get a z-score. That z-score is way to the left. So we're going to shade to the left because it's a left-tailed test. See the less than sign? We shade to the left. You can use normal CDS if you want, but it's going to be very, very tiny. We get a p-value of 0. Check into the next video to see how we're going to interpret all this.